Good morning. So this is our 34th session, and in the previous lecture we have started discussion on the pressure drop. Okay. So while we were discussing the pressure drop, two important things we have found that if pressure drop is proportional to velocity, then we have laminar flow. If it is proportional to velocity raised to power 1.75, then we have some other design which we call as turbulent flow, and the transition from laminar to turbulent flow inside a pipe depends upon the Reynolds number, and for a smooth circular pipe this transition nearly initiates at Reynolds number nearly equal to 2300, and it gets converted into the turbulent flow, fully turbulent flow, once Reynolds number becomes more than 10,000. Okay, and what we have to do now is that we had earlier also derived this head loss HF for particularly the generic formulation of the head loss is nothing but delta P by rho G plus delta Z. Okay, and whenever we try to calculate this head loss by doing the balance of forces along the stream direction, then we found that for Reynolds, particularly for this laminar flow conditions, it has become equal to 32 mu V into L divided by rho G d square. Okay, so this was the formulation which we have calculated for laminar flow. Now I told you that what we need to do, we need to write some formulation of the head loss which is actually more generic. It means the single formulation can take care of both the laminar as well as the turbulent flow. Okay, because we know that pressure drop is directly proportional to velocity for laminar flow and directly proportional to velocity power 1.75 for turbulent flow. It means that relationship between velocity and pressure drop is different for different types of flows. Okay, of course this relation 32 mu VL by rho G d square we have obtained after we substituted the parabolic velocity profile for a pipe flow, which is only applicable for fully developed laminar flow. Okay, so that's why what we need to do, we need to get some equation, some generic equation which can be applied for both laminar as well as the turbulent flows. Okay, so in that attempt, this scientist Wisbach, he proposed one equation according to which this HF can be written as F times L V square upon 2GD. Okay, where these parameters are clear to us. L is length of the pipe, V is average velocity of the flow, G is acceleration due to gravity, and D is diameter of the pipe. But we have this one additional factor F. So F, he proposed that F is nothing but function of Reynolds number of the pipe when it is calculated based on its diameter. Okay, and second effect, it is also dependent upon the relative roughness of the pipe, and it is also dependent upon the shape of the duct. So these three functional dependencies were taken. Okay, so what is the value of F? It will be depending upon all these three parameters. Reynolds number of the flow, okay, it will be dependent upon relative roughness, where this epsilon is nothing but called as absolute roughness. Okay, so what is the meaning of absolute roughness? Can you tell me? Say if I have this surface, but this surface is not perfectly smooth, it is having some irregularities, this type of irregularities. Okay, so what I can do, I can define some mean line which I will be considering as a equivalent smooth surface, and with reference to this mean line, whatever the upward and downward deviations I will be having, these I will be calling as nothing but epsilon, absolute roughness of the pipe. Is this point clear? What I am trying to say? So whenever you will be going for the industrial scale manufacturing, you cannot always ensure that you are having completely smooth pipes. There will be certain defects on the surface of the pipe and if we quantify these defects, that we can quantify based on the absolute roughness. Okay, and of course if we have the rough pipe, that will be introducing certain effect on our what? Pressure drop characteristics. Okay, flow characteristics and pressure drop characteristics. How it will introduce this particular effect was initially studied by Henry Darcy. So basically this Wiswech, he just proposed the equation, and the effect of roughness on surface characteristics was proposed by actually Henry Darcy. That is the reason many times we call this friction factor also, whatever this F I have introduced into the generic equation of pressure drop, this particular factor is also called as Darcy friction factor. Okay, we also call this factor as nothing but Darcy friction factor. Okay, so now till now I have got the generic equation. As per this generic equation, my HF is equal to F into LV square by 2GD. And for laminar flow conditions, I also know that my pressure drop is nothing but equal to, or head loss is nothing but equal to 32 mu LV upon rho G D square. Okay, so I can equate this. So this is coming from the fundamental theory. Once what I have done, I have actually calculated the pressure drop by considering the parabolic velocity profile, and this first one is coming from the formulation which was proposed by Wiswech for all types of flows. Okay, so in this equivalence, what I will be getting, my length will get cancelled. Okay, one velocity will get cancelled over here, then once again G is also cancelling out, and one diameter is cancelling out, and ultimately I am getting F is equal to 64 mu upon rho Vd. Okay, so we know that mu upon rho Vd is what? Reynolds number, which is calculated based on the diameter of the pipe. So I can say that Darcy friction factor for laminar flow is equal to 64 divided by Reynolds number of the flow. Okay, so one important point we are finding from here is that Darcy friction factor for laminar flow is independent of the roughness. It is independent of pipe roughness. Okay, it is independent of pipe roughness for what type of flow? For laminar flow. Fine. And why is it so? So if you see from the physical aspects, you will be finding that if you are having, say, these type of irregularities in the surface, because in laminar flow our path lines of the fluid motion will be having perfectly or smoothly aligned. Okay, so because of that my flow will move like this, and in these cavities I will be having presence of some fluid which will be actually remaining inside. Okay, and this will not create any disturbance for the layer which is moving just adjacent to the rough surface of the pipe. On contrary, if you talk about turbulent flow, in case of turbulent flow, what will be happening? If you have surface irregularities, because your flow streamline is not regular, so it may happen that flow is entering here, then it is being hindered by this wall, then because of that it is deflecting something like this. So because of this it will create lots of turbulent eddies over here, and these turbulent eddies will try to create the additional pressure drop. Okay, so it will influence the pressure drop. So that is the reason sometimes even if our actual pipe is physically rough, but if my flow is under the laminar flow conditions, then effect of Reynolds number is not coming into picture, then we call this pipe sometimes as hydrodynamically smooth pipe. Meaning is clear? Is this point clear? Though in reality our pipe is rough, Okay, but its hydrodynamic effect under the laminar flow conditions is that this roughness is not contributing into the pressure drop. So that's why we can call under the laminar flow conditions even our actual rough pipes also as hydrodynamically smooth pipes. Is this point clear? Okay. Now we have done this discussion on this one, and we came to know that if I plot my Darcy friction factor as function of Reynolds number, because it is coming in inverse relation with the Reynolds number, so it will be decreasing linearly with the Reynolds number. Okay, but this relation will be only applicable for a circular smooth pipe till my Reynolds number is nearly equal to 2300. I cannot extend after this, because after this the effect of roughness will also come into picture, and also what will happen? If I have to estimate the value of f, then I have to determine that what type of dependence on Reynolds number is coming for the turbulent flow. Okay, so it means that up to Reynolds number we are up to this laminar flow conditions, critical Reynolds number of 2300, we are able to develop a good understanding in between the friction factor and the Reynolds number, and if friction factor is known, then I can say a good understanding in between the pressure drop and the velocity condition or Reynolds number. Okay, but when my Reynolds number becomes greater than 2300, it means if I enter into the turbulent flow conditions, then what will be happening? Okay, so to know that, what we have to do, we have to first understand the theory of turbulence. Okay, so theory of turbulence is actually very complicated, and if you want to know, we are not having even the full absolute theoretical understanding of the turbulence. What we have some semi-empirical theories which people have developed in the past, and whatever the theories which have worked well, these has become actually the fundamental theories of turbulence even till date. Okay, so turbulence itself is a semester long course. Of course we will not go into that much depth, but if we have to relate, just say if your interest is after studying this course of fluid mechanics, at least you should be able to determine the pressure drop which is for fluid flow within different pipes. So in different industrial applications you will be finding that your flow conditions will be turbulent only. Okay, so by just knowing the pressure drop relationship for laminar flow, you cannot complete your knowledge, okay, from the application point of view. So that's why what we will do, we will try to present over here a very brief idea of turbulence, and then we will majorly see that how this brief idea of turbulence actually gives us the detailed understanding of friction factor and the pressure drop characteristics. And those who are more interested in knowing the turbulence, they can refer to advanced books for turbulence. Okay, so when we will be talking about the turbulent flow, I already told you that in case of turbulent flow, what we will be having, if I am at a single location also, and I am measuring velocity at single location, and if I plot that velocity as function of time, that will not be a unique value. Okay, my value of velocity will keep on changing with time. So this blue colored line over here shows the variation of velocity for one dimensional flow. Okay, and then similarly if I try to plot the pressure, pressure is also varying in the similar fashion. So any parameter if I consider other than the fluid properties, there we will be finding that we will be having variation of actually fluctuations with time as well as with the space. Okay, now if we have to come to some point where actually we can uh, solve these equations, so what I can do, I can divide this component of the velocity into two parts. Okay, so first thing what I have done, I have drawn a dashed line over here which is representing the average representative of mean flow. So that I have given as u bar, and any deviation from this mean velocity at every point we are calling as u dash. Okay, so now I can represent my actual velocity of the flow as nothing but mean flow velocity plus fluctuating component. In a similar fashion, for any other parameter which shows fluctuations during the turbulence, there also I can define that absolute value of that parameter will be nothing but the mean flow parameter plus fluctuation. Okay. Now, second important point is the major issue in case of turbulent flow is determination of the fluctuating components. Okay, because fluctuating components are very chaotic. There is no any specific arrangement, no trend which can mimic these fluctuations. Okay, so that is why whenever we will be doing the analysis, if we consider the fluctuating components into our analysis, or if I consider the actual velocity u or actual pressure p, because it is including the fluctuating components, so it will be becoming very challenging for me to find out this. Okay, so that's why what we do, we define some time average mean parameter and we try to solve our governing equations for these mean parameters. And along with these mean parameter, if any fluctuations are to be accounted, then we try to develop some semi-empirical theories for these fluctuations so that we can easily approximate these in terms of mean parameters. Okay, so that is the whole idea of turbulence. So what I will do, in order to find out u bar, I can say that I will be considering 1 by t, where t is some averaging time period, and this I will be doing integration from 0 to t. Okay, and here this u bar, because I am calculating u bar now. Okay, so it will be becoming nothing but u times dt. That is the simple meaning of u bar. What I have done, I have considered some time scale, and in this time scale region, whatever the variation of velocity is, I am integrating that with time and then dividing with time. So that will be coming as nothing but my mean flow velocity. So mathematically, whatever this dashed black colored line is there, mathematically it is computed from this relation. Is this point clear? Over here, whatever my t is there, so this t should be sufficient time so that it is able to account for enough fluctuations in the flow. Is this point clear? My t should be such that if I consider, say, only this much portion for averaging, then my mean flow will go somewhere over there. That is not correct. Okay, I have chosen very small time. So whenever I will be choosing this time t, it should be sufficiently larger than the time scale of the turbulent eddies. So time scale of turbulent eddies, the small fluctuations nothing but represents the time scale of turbulent eddies. Okay, so my averaging time period should be sufficiently larger than the time scale of the turbulent fluctuations. Is this point clear? Now another important point is, in case of microscopic or molecular theories, we say something mean free path. So whatever the role of mean free path is there, so that part, similar type of scaling comes in case of turbulence, which is called as mixing length. Okay, so what is the role of mixing length? That also I will be explaining to you later. But one important point is, when we are considering the time scale of turbulence, we have to consider it that it should include sufficient number of, or it should be sufficiently larger than the time scale of turbulence. Okay, so u bar we have calculated. Now if I want to calculate the u dash bar, what will be u dash bar? U dash bar will be 1 by t integral from 0 to t, and u dash is nothing but u minus u bar times dt. Okay, what will you get out of this? Can you tell me? 1 by t u dt will become u bar. Okay, and in the second term u bar will be constant because it is time dependent parameter. Integral dt will become t will cancel, it will become u bar minus u bar, which is equal to 0. So one important benefit which we are getting out of this decomposition of the velocity, or which is also called as Reynolds decomposition or Reynolds time averaging, that if I have to take the mean of the fluctuating components, that comes out to be 0. Okay, mean of fluctuating components is coming out to be 0. But if you take the u dash square and its mean, then it will be non-zero. Okay, you can mathematically check it. If you do u dash square of the fluctuation, and then if you calculate its mean, then it will be non-zero. Okay, similarly, if you do the product of fluctuation, say u dash and v dash, and if you calculate their complete mean, that also will be non-zero. Okay, so these are the some of the things which we are getting from this Reynolds averaging. Now what we need to do, we need to substitute this Reynolds averaging into our main governing equations to obtain the Reynolds average equations or to obtain the mean flow equations. Okay, so what is my actual continuity equation? Del u by del x plus del v by plus del w by, okay, equal to 0. Now in this I need to substitute this u with u bar plus u dash, v with v bar plus v dash. Okay, so if I do these substitutions, then ultimately I will be getting my continuity equation for turbulent mean flow as del by del x of u bar plus del by del y of v bar plus del by del z of w bar is equal to 0. Is this point clear? So I am not doing this mathematical substitution over here in detail, but what I am trying to say you that once I substitute this Reynolds decomposition into my mean flow, then ultimately I will be getting this as my mean flow or Reynolds averaged continuity equation. Is this point clear? Similarly, if you substitute for one dimensional flow, if you consider that you are having flow is dominant in only x direction, okay, then I will be mainly interested in only x momentum equation. I will not have much interest in y and z momentum equation. So if I want to obtain the x momentum equation, then I will be getting, after substituting this Reynolds averaging into x momentum, original x momentum equation, I will be getting rho times du bar by dt minus del by del x of p bar plus rho gx plus del by del x times mu del u bar by del x. So up to this we have seen in our actual equation also. But here I am getting one more additional component, which is rho u dash square and its bar, its average. Similarly, in del by del y term, up to this we know, but one additional term I am getting rho u dash v dash bar. Okay. Similarly, in the third parameter I am getting rho u dash w dash bar. So it means that this term we were knowing that okay, it is nothing but viscous stress. It is coming because of the viscous stress. Okay. But what about these terms? Rho u dash square, rho u dash v dash, rho u dash w dash. These terms are nothing but called as the turbulent stresses. Okay, these terms are called as turbulent stresses. In physical sense, if you see what these terms are representing, these are representing rho times some velocity field. Okay, so rho times some velocity field nothing but represents the acceleration of the fluid particle. Okay, so physically these are nothing but showing the random accelerations of the fluid particles. But mathematically these terms are having dimensions identical to that of the stresses. That's why we call these as turbulent stresses. Is this one clear? Physically you can see whenever you will be having the random fluctuations in the flow. So because of the random fluctuations in the flow, whatever the random acceleration of the fluid particle is taking place, these random accelerations are accounted for in these terms. Okay, but these terms are having dimensions identical to the stress terms, and these are coming with stress terms into our governing equations. That's why we are calling these as turbulent stresses. Okay, and many times many literatures, many books of the turbulence also call these terms as Reynolds stresses. Okay, so many times these are also called as Reynolds stresses because these terms have come into governing equations after we have applied the Reynolds averaging on our actual or original Navier-Stokes equations. Is this point clear? So, one important thing we have got is that mean flow estimation is identical to the calculation of the Navier-Stokes equations for laminar flow. Okay, mean flow is identical to what we are solving in case of laminar flow. The only thing is that whatever these additional turbulent stress terms are now appearing into our flow. So if I have to solve the Navier-Stokes equations, I should have some criteria whose help I can take to determine these particular terms. Okay. So how to solve these particular terms? There are lots of approximations. Maybe I will not go into that detail, but this is the original idea that when turbulence comes into picture, then along with the mean flow parameters, we are also having some additional parameters into our governing equations which are called as turbulent stresses. Okay. Up to this point, is it clear? Okay, now what I can do, this is the previous equation only. I have written this equation, rho du bar by dt is nearly equal to minus del p bar by del x plus rho gx into del tau by del y. Because I told you that I am writing these equations only for one-dimensional flow. If I consider one-dimensional flow, then I will say that the variations along x direction of mean velocity and variation along z direction of mean velocity will be negligible. Okay, so in that case I will be having only the variation along the y direction. So if I consider only this y direction variation, then I can write my stress equation something like this, where this stress tau will be equal to mu times del u bar by del y, which is identical to the laminar component. That's why I have written it as tau laminar. Okay, and this rho u dash v dash is the turbulent component which I am writing as tau turbulent. Up to this point, is it clear? If I consider one-dimensional flow, turbulent flow close to a wall, okay, only as I am specifically mentioning that my mean flow is only one-dimensional. So if my mean flow is only one-dimensional, then I will not be having any variation of mean flow in x and z direction. So that's why I have only considered the y term over here. Okay. So because of this turbulent component, I have now got in my stress term, particularly my viscous stress term, I have got two components. So this one is laminar component, one is turbulent component. But you can see that in the stress components, the molecular viscosity dependent component is only laminar stress, whereas the turbulent stress is actually independent of the molecular viscosity. It is not dependent upon molecular viscosity. Is this point clear? All are clear with this idea? Basically what I am trying to say is that if I have total stress as tau, that total stress is nothing but combination of the laminar stress plus turbulent stress. So that is the whole idea of this particular equation. Okay, all are clear with this? So now wall bounded flow is taken. So you can see this bottom portion is nothing but a solid wall, and say if I plot wall shear stress within the boundary layer. So if I have a wall, of course it will be having some boundary layer. So I have taken actually zoomed view of this wall, and this delta x, y equal to delta x is nothing but representing the location of boundary layer thickness. Is this point clear? Means only within this point I will be having the existence of gradients, and outside this point my flow will be invisible. Okay. Now if I plot the shear stress, we know that shear stress will be having highest value at the wall. So that's why I am calling this as nothing but my wall shear stress at this location X. So this solid line over here shows my value of total stress tau xy. Okay, and of course in this tau xy I have how many components? Two components. One is laminar component and second is turbulent component. So if I, in this total stress tau, if I try to see now the contribution of laminar component and the turbulent component, I will be finding that this dashed color line over here shows the magnitude of the laminar stress. Okay, if dashed line is the contribution of the laminar stress, this term, then total minus this term will be nothing but contribution of the turbulent component. Is this point clear? So one interesting fact you will be finding that in the region very close to the wall, say somewhere up to this point you will be finding that in our total stress contribution the majority is coming from laminar flow. Okay, and turbulence is having very small effect in the region very close to the wall. Is this one clear? Then I have some intermediate region, particularly say up to this point, where I am having laminar as well as the turbulent component, both are having almost equal contribution. Okay, similar contribution. Then I enter into the region which is significantly away from the wall, where laminar contribution is almost zero, and this entire contribution is because of the turbulent stress. Is this one clear? So it means that in a wall bounded flow, I can divide my region into three parts. One region very close to the wall, very small thickness but very close to the wall, where still, though my complete flow is turbulent, but still in that particular region the major contribution is coming from the laminar stress. Okay, that's why I will be calling this particular region as viscous wall layer, or in many literatures this is also called as laminar sublayer. Is this point clear? So even if you have turbulent flow, in turbulent flow also there will be some region which is very close to the wall, where our stress, total stress is majorly coming from the laminar conditions. Okay, that's why we will be calling this particular region which is viscous dominant, because this first term is viscous dominant, second term is not having any contribution of viscosity. Okay, so where we have viscous dominant stress, that we call as viscous wall layer or laminar sublayer. Then outside region, where we have almost equal contribution of the laminar component and the turbulent component, that we call as overlap layer, or many literatures call this as buffer layer as well. Okay, so in many textbooks or papers you will be finding it is written as buffer layer. And then ultimately we have outer turbulent layer. Okay, in this outer turbulent layer, of course, what we will be having? We will be having major contribution because of the turbulence, and contribution of laminar portion is actually very, very less. Okay, so actual turbulent portion is one in which the effect of molecular viscosity is not there. So in this region you can say that the laminar contribution is zero. It means this viscous component is becoming equal to zero. So is this point clear? So molecular viscosity is not playing any role. So that is the major reason for presence of significant amount of turbulent eddies. Okay. So this is called as outer turbulent layer.
So in this case, the dotted graph is being shifted up, each for different values of y, which give different lines.
This dotted graph you are trying to say?
Yes.
No, what I am trying to say, you can see that this dotted graph is nothing but my laminar stress. This is my total stress. So if this dotted is approaching the reference line, it means up to this zone I don't have any laminar stress. So here whatever the stress is coming, that is only because of the turbulent contribution. Have you understood now? Okay, so because of this thing I can divide my reason into three parts. Okay, so I can say that in this viscous wall layer I should have some different variation of the velocity, because it is having some different kind of gradient which is existing. In this zone I must have some different variation of the velocity field, and in this zone I must have different variation of velocity field. So it means that in a turbulent flow, if I have to completely define the velocity field within the boundary layer, I must have three different mathematical formulations to specify the velocity field. Point is clear? Okay, because my whole zone is having three different types of physics involved. If there are different types of physics involved, so obviously to transform these different types of physics into mathematical relations for the velocity field, I also must have different laws for explaining the variation of velocity along the y direction. Is this point clear? All are clear with this idea? Okay, so that is the next part. So you can see now we want to see the velocity profile in turbulent flow. Okay, so first reason I told you, near the wall where viscous effects are dominant, wall shear stress is mainly contributed because of the laminar flow. So I can consider a functional form that velocity in this region will be function of molecular viscosity, wall shear stress, density and distance y along the vertical direction. Okay, and if I apply now dimensional analysis on this formulation, I will be finding all these parameters are finally becoming only two dimensionless parameters, where I have u plus is dimensionless velocity, which is equal to u by u star, where u star is nothing but tau w by rho and square root of this, and this is called as friction velocity. Why it is called as friction velocity? Because it is majorly coming, if you see the formulation, it is coming because of the wall shear stress. Okay, so we call this as friction velocity. So it means that if near the wall I divide my flow velocity by friction velocity, then whatever the velocity I am getting, that I am calling as u plus. Okay, and this u plus has become function of y times u star by nu. What is nu? Kinematic viscosity, mu by rho. So this term now you will be seeing, it will be coming as a dimensionless distance. So that's why we call this y u star by mu as some value called as y plus. Is this one clear? So dimensionless vertical distance I am calling as y plus. So this type of functional formulation will be applicable only in which region? The region which is very close to wall. So that's why this is also called as, this first formulation is also called as law of wall. So it is called as law of wall. Point is clear? So first reason we have targeted. Then we will be considering now the region which is completely outside. Okay, outer region of the boundary layer. Means I am referring to this particular region which is outside the buffer layer. Okay. So here main free stream velocity is u, and inside the localized velocity will be small u. So in the outside region we will be finding that u minus u near to the boundary layer region, it is a function of some g is another functional form, function of delta, because we are trying to estimate this velocity nothing but close to the boundary layer thickness. That's why I am writing this delta over here. Then of course wall shear stress and density and y. So in this point I am not including the effect of molecular viscosity, Is this point clear? Because away from the wall, close to the boundary layer near the wall region, my velocity is not dependent upon molecular viscosity. So that's why when we are writing this functional form, we are not including over here molecular viscosity. Okay. Once I apply the dimensional analysis over this, I will be getting that u minus u by u star, where u star is identical to what we have calculated in the previous one, tau w by rho power 1 by 2, is equal to g of y by delta. So it means some other function which is showing the y by delta, function of y by delta dependence. Okay. So this particular law is called as velocity defect law. Okay, so important point that near the wall we have different functional form of velocity and vertical distance, which we call as law of wall. Then in the outer region, which is close to the boundary layer, I have different relationship in between the velocity and the vertical distance, and this relationship is particularly independent of the molecular viscosity, and it is called as velocity defect law. Point is clear? Now, I should have some formulation which is actually merging the two regions. Okay, for overlapping region also I should have some formulation which will be able to give the smooth transition of velocity. Okay, so how to obtain this smooth transition of velocity? So this smooth transition of velocity, mathematically it was seen that if I consider u by u star and if I consider some logarithmic variation of this, so 1 by k is some, this k is some constant, and ln of y u star by v means ln of y plus, this is called as y plus, and plus some intercept I add b. Then if I consider the values of these constants nearly equal to 0.41 and 5.0, then I will be getting some logarithmic law, and this logarithmic law will bridge the gap in between outer layer and the inner layer to show a smooth transition of velocity. Is this one clear? All are clear with this idea? Okay, so let me plot these formulations and then let's see what happens. So what I have done, this side I have considered a logarithmic scale. So you can see this 1 to 10 to power 4 we are going. So this is my logarithmic scale. Okay, and this side I have linear scale. So it means this is my semi-log plot. So on this semi-log plot, I have plotted y plus, which is y times u star by v along abscissa, and I have plotted u plus along ordinate. Okay.
Sir, in the velocity defect law, what is the meaning of capital U?
Capital U is the free stream velocity which is outside the boundary layer. Okay, the constant value of velocity, because outside the boundary layer your flow is inviscid. So if flow is inviscid, then you will not be having any variation in the velocity. It will be some unique value of velocity. So that is capital. Okay. So now I have y plus plotted along abscissa and u plus plotted along ordinate. Now these two, law of wall and this velocity deflection law, I have the functional relationship. So of course I have to determine these functional forms. So how we have done, for law of wall, we have simply written that u plus is equal to y plus. So it means both are having linear dependence. If both are having linear dependence, so of course on a semi-log plot it will look like a curve. Okay, so if it's a linear plot, then it will be looking like a straight line, but on semi-log plot it will look like a curve. So this is my curve. This dashed line over here shows the curve of u plus equal to y plus, which is nothing but linear, which is applicable for linear viscous sublayer. Then I have this straight dashed line. Okay, so I have this log term dependence over here with y plus. If I plot it on semi-log scale, it will be coming as a straight line. So this straight line over here is nothing but corresponding to the logarithmic overlap law. Okay, and these curves over here, so particularly for this outer region, velocity defect law, we have not plotted any functional form, but what I have done now, I have shown you over here a form line. So you can see this blue colored solid line. So this blue colored solid line is nothing but coming from the experimental measurements. Okay, so you will be finding this blue colored solid line for different situations. So if I have a wall bounded flow means close to the flow I have a solid wall. Okay, so in a wall bounded flow, if I have strong increase in pressure, it means when the flow is moving from inlet to outlet along the length of the wall, my pressure is actually strongly increasing. So if I have strong increase in the pressure, then within this inner layer and overlap layer, my velocity will be as it is, but in particularly in this outer layer, I will be having some change in the velocity. Okay. On contrary, if I have flat plate flow, so I have a solid flat plate and flow is happening over that. Then also my inner layer and overlap layer are not having any changes, but in the outer layer my flow is coming more closer towards the logarithmic law. For pipe flow you will be getting this line. This is the line for pipe flow. And for strong decrease in pressure, so if you have wall but along with that pressure is also decreasing strongly in the downstream, then your flow then your velocity profile approaches more closer to the logarithmic law. Is this point clear? So one important thing I can say over here, that up to the y plus value of nearly equal to 5, up to y plus value of nearly equal to 5, my experimental measurement is completely matching with the linear viscous sublayer law. Is this point clear? And somewhere y plus close to 30, y plus close to 30, my experimental measurement is exactly matching with the logarithmic law or overlap law. Is this point clear? And the reason in between y plus equal to 5 to 30 is something where I have to get some transition in between linear law and the logarithmic law. Is this point clear? So up to y plus nearly equal to 5, I have linear dependence on velocity, and when my y plus is close to 30, then it is closely matching with the logarithmic law. And in the outer layer, I can say that in the outer layer, my majority of the velocities are coming close to the logarithmic law, except for the region which is deviating along where I have strong pressure increasing gradient in the downward direction. Is this point clear? So other than that, my logarithmic law is coming in the picture. One simple assumption we can make out of this is that this y plus region will be very small in case of turbulent zone. Y plus up to 5 is very, very small. So if I neglect this very small region, I can say on a broader sense that my logarithmic law will be mostly mimicking the velocity profile in complete zone. Is this point clear? What I am trying to say? Because this laminar viscous layer or laminar sublayer thickness is very small, extremely small in comparison to the total boundary layer thickness. Okay, so that's why I can say that for these scenarios, I can simply assume my logarithmic law to be applicable for the complete boundary layer region. Okay, so it means that I can assume my velocity profile to be logarithmic for turbulent flow. So what we will do now, I'll stop at this point, and in the subsequent lecture, next lecture, we will try to see this logarithmic layer, how it actually, if we substitute it, then how it helps us in determining the friction vector. Okay.